Friends, this lecture focuses on statistical tests in research. It is a wide area and it may not be possible to do justice to statistical tests in one lecture, but I will tell you that basically what statistical tests mean is that when you get data on the basis of sampling, you would like to know whether the measures or indicators which are corroborating your hypothesis and reveal something statistically significant or they have arrived due to sampling fluctuations. For example, there may be a population in which two variables are independent and have no correlation. But when you draw a sample from the population, you will get some correlation coefficient between x and y, any two variables. It is a number, a matter of numbers. So, is that correlation coefficient meaningful? Can such a correlation arise even when in the parent population correlation coefficient is 0? Is it a matter of sampling fluctuations only, or does it lead credence to our research hypothesis? That is the subject matter of hypothesis testing, and all tests are designed around that. And I have some parametric and some non-parametric tests. Let me tell you what they are, and you decide. Maybe this lecture will not make you understand statistical tests fully, but they will tell you what are statistical tests about, and later on you can go back and read from the books more details about these tests. From Sidney Siegel's book, I find that objective procedure for hypothesis testing consists of the following steps. First, state the null hypothesis and its alternative hypothesis. Right in advance, we state both null hypothesis, that there is no correlation, and also the alternative hypothesis, that there may be a correlation, or the correlation is positive, or correlation is negative, or correlation is greater than this or less than this. Alternative hypothesis is actually your research hypothesis, and it may be stated in different forms, and then decide what data to collect and under what conditions. Second, from among the several tests with its associated statistical tests which might be used with a given research design, choose that test the model of which most closely approximates the conditions of research in terms of the assumptions on which the test is based. Specify a significance level, and we will talk about what is significance level, and a sample size. Find the sampling distribution of the statistical test under the assumption that H0 is true. It may be sampling distribution of a function of correlation coefficient or sample mean or sample variance. Find out the sampling distribution of the test. On the basis of 2, 3 and 4 above, define the region of rejection for the statistical test, that if the value of the test, which is a function of parameters which you want to test on the basis of sample data, for what values of those tests you are going to reject the null hypothesis. You may say that if my value of z is more than 1.96 or less than minus 1.96, or if the value of t is more than this, or if the value of f is more than this, then we will reject the null hypothesis. You specify a critical region and this is this in what area you will reject the null hypothesis is associated with your alpha or sometimes called P. Collect the data, using the data obtained from the sample, compute the value of test statistic. If that value is in the region of rejection, the decision is to reject H 0 and then accept H 1. It is not that after rejecting H 0 you will decide what H 1 could be. Your theory of your review of literature must suggest right in the beginning what is H 1, and you must also be prepared to accept or reject H 0 or reject or accept H 1. Truly speaking, there is nothing like acceptance of H 1. We are looking for rejection or acceptance of H 0. And if H 0 is accepted or rejected, in both cases you are ready with an interpretation. You are ready with explanation of why H 0 is accepted or rejected. If that value is outside the region of rejection, the decision is that H 0 cannot be rejected at the chosen level of significance. H 0 may be rejected at one level of significance and may be accepted at another level of significance. So, level of significance is important to specify. Now, what is null hypothesis? The null hypothesis is the hypothesis of no effect and is usually formulated for the express purpose of being rejected, that is the negation of the point one is trying to make. If it is rejected, the alternative hypothesis is supported. The alternative hypothesis is the operational statement of the experimenter's research hypothesis. Research hypothesis determines how H 1 is stated. So, H 1 if the research hypothesis simply states that two groups will differ with respect to means, then H 1 is that mu 1 is not equal to mu 2, but if the theory predicts that the direction of the difference, that is one specified group will have a larger mean than the other, then H 1 may be either that mu 1 is greater than mu 2 or mu 1 is less than mu 2. That is the mean for group 1 is greater than or less than the mean for group 2 respectively. Now, this is important to specify right in the beginning whether your alternative hypothesis is mu 1 is not equal to mu 2 or mu 1 is greater than mu 2 or mu 1 is less than mu 2, because your area of rejection is going to be decided by your alternative hypothesis. There is a close connection between alternative hypothesis and the critical region. Critical region may be on both sides of the distribution or one side of the distribution, and how much on one side how much critical region will exist will depend on what is the nature of the alternative hypothesis. The next step is to specify alpha. A subset of samples that are so inconsistent with H 0 that the probability is very small when H 0 is true, that the sample we actually observe will be among them. And then if we actually observe a sample which is included in that subset, we reject H 0. So, for any given value of alpha, we specify a critical region, so that if the sample point, if the calculated value of the test falls in the critical region, we reject the null hypothesis. This is an example of two-tailed test, where critical region is on both the sides, and if the value of the measure is more than this or less than this, in both cases we are going to reject the null hypothesis. It may be said that alpha gives the probability of mistakenly or falsely rejecting H 0, in medical terms false positive. It is also called a type 1 error. There are two types of errors. See, either your null hypothesis is correct or it is incorrect, and on the basis of study of your sample and critical region on the distribution under the assumption of H0 or null hypothesis, you are going to decide whether null hypothesis is accepted or not accepted. If null hypothesis is true and it is accepted, then it is okay. If null hypothesis is true and it is rejected, there is an error. This error is called alpha, and if the alternative hypothesis is true and null hypothesis is accepted, then also there is an error. That error is called beta. We will mention about this error a little later. And if alternative hypothesis is true and alternative hypothesis is accepted, means if null hypothesis is wrong and null hypothesis is rejected, then it is okay. That is called power of the test. We have another, so type 1, type 2. Type 2 error of beta, which is the probability of accepting the null hypothesis when it is false or when the alternative hypothesis is true. Now, it can be shown graphically as well as mathematically that reduction in type 1 error would lead to increase in type 2 error. It is not possible to minimize both types of error simultaneously. What I was telling, that the aim of statistical testing is to ensure a high power of the test, means probability of rejection of null hypothesis when it is wrong or when alternative hypothesis is correct. So, power is 1 minus probability of type 2 error or probability of rejecting the null hypothesis when it is false, that is when the alternative hypothesis is true. Power is also called the strength of the test. Power depends on alpha, on sample size, on difference between true value of the parameter, means the difference in the value of the parameter under null hypothesis and alternative hypothesis, and whether you go for one tail test or for two tail test, and the value is specified by H0. Several things. Power depends on several things. This figure shows the difference between type 1 and type 2 errors pictorially and makes it more clear. Like this distribution is distribution under the null hypothesis, and on the basis of alpha equal to 0.05 or 5% level of significance, you fix this red color critical region on one side of the distribution. Okay. So, you decide that it is a one side test, and there is a value, this value of test, if on the basis of alpha or 0.05 you are deciding if the value of the test is less than this on the left hand side of this point, then you will accept the null hypothesis, and if the value of the test is on the right hand side of this point, then you are rejecting the null hypothesis. It is simple. Now, imagine that there is another distribution, this distribution. This is the distribution of the same test under alternative hypothesis, when alternative hypothesis is true. Like this is for null hypothesis about mean, like mu equal to 5, and this is for the alternative hypothesis that mu is 9, 5 and 9. Then imagine that the value of your test is less than this, you are going to accept the null hypothesis. But do not you find that there is an area, this yellow color area, which is on the left hand side of this point when you are accepting the null hypothesis, but this area also falls under the alternative hypothesis, which means that this total area is the probability of acceptance of null hypothesis when it is actually false. In all decisions there are errors of both the types. on the basis of certain pathological measures or other kinds of tests, a doctor has to decide whether a patient is suffering from something or not. Now, only God knows whether the patient is suffering from something or not. If the patient, a doctor can make two types of errors. Patient is not suffering from something and doctor diagnoses on the basis of empirical data that the patient is suffering, that has a cost. The patient has to take in medicine, the patient has to take maybe surgery, and that has a cost in money terms, in physical terms, emotional terms. And it is also possible that the person is suffering from something, but still the doctor says by looking at the data that the person is completely okay. That also has a cost. Then the problem may aggravate further and that may cost more money or more stress later on, but not today. Today the patient will feel happy. So, there are both types of error. Our decision rests on this point. If our value of the test is on the left hand side of this point, we accept the null hypothesis. On the right hand side, we reject the null hypothesis. This area which falls under distribution with null hypothesis is one type of error, and this area which falls under distribution under alternative hypothesis. So, here we accept the null hypothesis, but null hypothesis may not be true, alternative hypothesis may be true, that is beta or type 2 error. 0.36 is type 2 error, and 1 minus point, what will be 1 minus 0.3628? 1 minus 3628 will be this larger area under the second distribution. What is the meaning of this larger area? The meaning is that we are rejecting the null hypothesis when it is actually false, that is good, and that is called the power of the test. There is another concept of power efficiency, that power of the statistical decision depends on what statistical test has been used. There are so many tests for the same purpose. Since it also depends on sample size, we can define that power efficiency equal to 100 Na divided by Nb percent. If test B requires a sample of say n equal to 25 to achieve the same power 1 minus beta as A with n equal to 20, then the power efficiency of B is 80%. 20 divided by 25 into 100, 80%. We often define asymptotic relative efficiency of test B as the power efficiency of B when n A tends to infinity. Now, sampling distribution. The distribution when H0 is true of all possible values that some statistic, say the sample mean, can take when that statistic is computed from many equally sized samples drawn from the same population. There is a central limit theorem in statistics which makes many of our tasks simple in sampling theory, and that is that if a variable is distributed with mean mu and the standard deviation sigma, and if the random samples of size n are drawn, then the means of these samples will be approximately normally distributed with mean mu, which is mean of the population, and standard deviation sigma by root n when n is large, capital N is large, population size is large. We have used this formula in some of the earlier lectures also, and this is the shape of the normal distribution. Decision: reject the null hypothesis if the sample falls in the critical region. I am repeating the same thing sometime because you are first time exposed to these ideas and there may be lot of confusion about some of these concepts. Note that the rejection of the null hypothesis is not same thing as proving the alternative hypothesis. Your aim is either to accept the null hypothesis or to reject the null hypothesis. According to philosophers like Karl Popper, you can never prove anything, you can only reject something on the basis of hard facts. Literature review, not the rejection of null hypothesis, helps in deciding the alternative hypothesis, because for the same null hypothesis you can have many alternative hypotheses. The region of rejection may lie on one side of the distribution as in one-tailed test, or on both sides of the distribution as in two-tailed tests. One-tailed tests have more power than two-tailed tests. Power, again to repeat, power means probability of rejection of null hypothesis when it is false. That power, there is more power, more probability of rejection of null hypothesis, a desirable property of testing when the critical region is defined on one side of the distribution only, means one-tailed test. One-tailed test is more powerful than a two-tailed test. This again shows one-tailed and two-tailed test. This is one-tailed test. In this one-tailed test, if the value of test statistic will be less than this, we will reject the null hypothesis. If it is more than this, we will accept the null hypothesis. For all values higher than this, we will accept the null hypothesis. This is two-tailed test, in which critical region lies on both sides. If the value of the test statistic is more than this or less than this, in both the cases we are going to reject the null hypothesis, otherwise we will accept the null hypothesis. Two-tailed test. This is one-tailed test. Okay. Tail on both sides, tail on one side. There are two types of tests, parametric and non-parametric tests. Parametric tests are more powerful than the non-parametric tests, but they should be used only when assumptions of parametric tests are satisfied. For small data, variables not on interval scale, logical and simple inference, non-parametric methods are preferred over parametric methods. For example, use Z for testing a null hypothesis like mu equal to mu 0 or mu 1 equal to mu 2, that means of two groups are same, or for a large sample correlation in the parent population is 0, etc. The observations are independent. You will use Z when observations are independent. Observations are drawn from normally distributed population. Actually, this is an important criterion which makes parametric test parametric. In the case of analysis concerning two groups, the populations must have the same and known variance, sample size is sufficiently large, the variables must have been measured on at least an interval scale, so that it is possible to interpret the results. Parametric tests will be discussed in different lectures later. We will talk about t-tests, f-tests, etc. In specific lectures on them. Today, I thought that when I am introducing hypothesis testing, I can mention about some non-parametric tests, because you have very little opportunity to go through non-parametric tests in literature. T and F, they are parametric tests. They are used for comparing groups. When you have two groups, you use t-test. When there are several groups, you use F, and this is part of an ANOVA, analysis of variance, AN for analysis, O for of, VA for variance, analysis of variance. For comparing two groups, you use T. For comparing three or more groups, you use analysis of variance and F test. Non-parametric tests, when the sample size is small, data are not so reliable, data are on ranks, means they are not on interval scale, and the assumption that the population from which the sample is drawn follows a definite distribution such as normal cannot be made. When you cannot make an assumption regarding the nature of distribution in the parent population, then you have to go for parametric tests. Then you have to go for non-parametric tests. So, parametric tests are used when sample is sufficiently large, when the data are reliable, when the data are obtained on interval scale at least, if not on ratio scale, and the distribution of the test is known. It is some standard distribution like normal distribution, chi-square distribution or T distribution or F distribution, some known distribution, uh, and the observations are drawn independently from the population. When any of these assumptions is violated, means when you are dealing with the small samples. In medical statistics, we often deal with the small statistics. Even in agricultural sciences, we deal with a small number of cases, small number of plots, a small number of farms, a small number of experiment and tests. So, in those situations or in studies of some very specific types of population, stigmatized population or people affected or people living with HIV, those kinds of things, or tuberculosis. You are studying number of tuberculosis cases in a government hospital in a district, number will be small. So, in all such situations you go for non-parametric tests. Some example of non-parametric tests are rank correlation. The other day when I was talking about correlation coefficient, I also mentioned about rank correlation. Rank correlation is defined as 1 minus 6 sigma d square by n cube minus n, while correlation was defined as covariance divided by square root of variance x, variance y. Rank correlation is used for non-parametric purposes. Then chi-square. Chi-square is both actually. Chi-square can be used or chi-square can be seen as a parametric statistic, because chi-square distribution is known, and we saw how in contingency table O minus E whole square divided by E follows a standard normal distribution, and sum of this expression for all the cells of a contingency table follows a chi-square distribution. But chi-square is also used as non-parametric test. Chi-square is both parametric as well as non-parametric. Then Mann-Whitney test. Mann-Whitney test is used to compare two samples. Median test to compare two samples. Sign test, we will see what these tests are. In short, in one minute maybe I will try to cover all these things to give you a basic idea about what these tests are. Run test, also known as Wald-Wolfowitz test, and Fisher's exact probability test, about which I mentioned when I was talking about chi-square. Mann-Whitney test first. The null hypothesis in a Mann-Whitney test is that the two distributions, you have two distributions, they are identical or their means are same. The alternative hypothesis is that the two distributions differ, but only as regards their mean or other measure of location, say median. They differ with respect to median and not with respect to other parameters. And it is a distribution free test. You do not make use of any distribution in the population. You do not assume that the observations come from populations which are normally distributed. Now, this is the statistic. In Mann-Whitney test, this is the test statistic u equal to S1 minus N1, N1 plus 1 by 2. S1 is the sum of ranks of observations under one distribution in the pooled data. For null hypothesis to be rejected, u must lie beyond u alpha by 2 and u 1 minus alpha by 2. Let me explain this thing. What it means that you have say number of children in two classes of people, upper class, lower class, number of children, upper class, lower class. So, there are two groups, and you have n1 number of cases in one group, upper class, and n2 number of cases in the lower class. Now, you pool the data, forget about upper class and lower class, and for all the values of number of children, you rank them, okay, and then separate ranks of observations which belong to one group, say upper class, from ranks of individuals who belong to second group, lower class. Add them. Sum of their ranks separately in the two groups is S1 and S2. Then test statistic is U equal to S1 minus N1 N1 plus 1 divided by 2. Those who are familiar with algebraic series can see that this N1 N1 plus 1 by 2 is nothing but sum of N1 natural numbers. The two groups are very extreme, then sum of extreme means there is nothing common, then sum of ranks of the first group can be N1 N1 plus 1 by 2 if the ranks are 1, 2, 3, 1, 2, 3 up to N1. All the ranks 1, 2, 3 up to N1 are of respondents who belong to group 1 or upper class. And S1 is the sum of ranks of observations. S1 is actually the sum of ranks of observations in the upper class, that is S1, and this is what would be if first group is so separated from the second group that ranks 1 to N1 belong. This is an extreme case. This will happen when they are just separated, there is nothing common. And if then like t test or z test, we also have to identify two values beyond which we will reject the null hypothesis. What is null hypothesis? That the two groups are same. What are those two values? One value will be this, u equal to this, another value will be N1 and 2 minus u alpha by 2. So, if your calculated value lies between u alpha by 2, u alpha by 2, alpha is like alpha may be 0.05. So, you will look at u 0.025 in the table for N1 and N2, separate tables are prepared for u. Your calculated value of u lies, this u calculated, this is calculated value of u. If this value lies between this and this, then you accept the null hypothesis. If your calculated value u is less than this or more than this, then you will reject the null hypothesis, as usual the rule for acceptance or rejection of null hypothesis. Actually, what it means that if your capital U, observed value of u lies between this and this, then the two distributions are mixed, and therefore, you cannot say that one is different from the other, they are same. Null hypothesis is that they are same, they are not different.
Now, let us take an example. There are two series, series 1 and series 2, which show data from samples of size 6 in each case, and let the measures be 7, 21, 9, 4, 50 and 55 in series 1 and 2, 3, 8, 1, 17 and 0 in series 2. According to Mann-Whitney test, we combine the two series, we pool the data and then find out ranks of all these values in the pool data. Pool data are arranged either in ascending order or descending order, and ranks of each value are obtained. Now, for example, in this case, the ranks of values of series 1 are 6, 10, 8, 5, 11 and 12. The sum of these ranks is 52, and therefore, u, which is defined as sum minus n plus 1 by 2, is 52 minus 6 into 7 divided by 2 equal to 31. Now, for these values of N1 and N2, 5% limits of U Mann-Whitney test critical values are 6 and 36 minus 6 or 30, which means if the calculated value lies between 6, this 6 and 30, then at 0.05 level of significance or 0.05 level of significance, the null hypothesis is accepted. But if the value of U lies beyond the range of 6 to 30, it will be rejected. Now, in our case, the value of U is 31, and therefore, the null hypothesis that there is no difference between values in series 1 and values in series 2 stands rejected.
Okay. Then median test. Median test implies this, that there are two groups and separate observations in those groups, and combine them, calculate the combined median of the combined or pooled data, and then find out what proportion of observations in group 1 and group 2 are above the median or below the median, does not matter. So, P1 is the proportion of observations in group 1 which are above the median of the pooled data, and P2 is the proportion of all the observations in group 2 which are above the median of the pooled data. Let T be defined like P1 minus P2 divided by square root of P1 minus P 1 upon N1 plus 1 upon N2. There P is this proportion, P is proportion obtained by this formula. And those who are familiar with standard error of difference of proportion, they can see that this denominator is nothing but standard error of proportion if the estimate of proportion in the population is P. So, P1 minus P2 divided by standard error of P from two samples with sizes N1 and N2. In one group it will be P1 minus P divided by N1, another group it will be P1 minus P divided by N2. So, standard error of P1 minus P2 will be this if they are independent, and as long as no observation is less than 5, T can be assumed to follow normal distribution with mean 0 and variance unity. In the above example, common median is 7.5 and the two P's are 2 by 6 and 4 by 6. The example which I have just shown, in that example there are two observations above the median in first group and 4 observations above the median of the pooled data in the second group. So, the common P is half and T is 2 by 6 minus 4 by 6 divided by root 0.25 by 12 equal to minus 2.29. Now, the null hypothesis is rejected because in a normal distribution minus 1.96 is that value below which 2.5% area lies. So, in two-tailed test with P equal to 0.05, the null hypothesis stands rejected as minus 2.29 is less than minus 1.96. So, this is median test. What median test is doing is that it is calculating median of the pooled data, then calculating what proportion of cases lie beyond that median of the pooled data separately in the two groups. And if the difference between two proportions P1 and P2 is statistically significant, then we say that null hypothesis of non-difference, Null hypothesis is, or as I said earlier, is always stated in the form that there is no difference between two groups, or there is no correlation, or there is no effect of this thing on that thing. So, in this case the null hypothesis that there is no difference between two groups stands rejected. And according to normal distribution theory, here we are using making use of several things. We are making use of normal distribution for t. So, but you can't call it a parametric test because we are using a normal distribution, because the logic of test is derived from here. It is simple. We expect that if two groups are similar, then proportion of cases above the median of the pool data should be same in both the cases. This logic is part of non-parametric, and for large samples, if as no observation is less than 5, this t follows a normal distribution. That is the second part. So, it is a kind of triangulation. Yes, sociology students are very much familiar with the idea of triangulation. Triangulation can be triangulation of theory, it can be triangulation of methods, it can be triangulation of statistical measures or statistical tests also. It is a kind of triangulation of parametric and non-parametric. The idea that make the pool data and calculate proportions in both the cases separately our median of the pool data. This is the part that that comes from non-parametric understanding. Here you are not making any assumption regarding distribution from which samples have come, but using the idea of normal distribution for large values of n, and here normally large is defined as low as 5. If no observation is less than 5, then t can be assumed to follow. These non-parametric tests in one way are sort of ad hoc, practical, pragmatic, commonsensical tests, and the power of such tests is obviously lower than the power of parametric tests. Fisher's exact probability test for the contingency table. You have seen chi-square test for contingency table. Let this be a contingency with 4 cells, and the cell frequencies be A, B, C and D. Sum of the two columns is A plus C and B plus D. Sum of the two rows is A plus B and C plus D, and the grand total is n. This is contingency table, that means A, B, C, D are numbers. They are not the values of the variable, they are numbers. Fisher showed that marginal totals being fixed, the probability of getting this configuration A, B, C, D means if A plus B, C plus D, A plus C, B plus D and n are fixed, then the probability that your contingency table will have the configuration A, B, C, D is this probability. This is factorial A plus B, factorial C plus D, factorial A plus C, factorial B plus D. What they are? A plus B is total of the first row, C plus D is total of the second row, A plus C is total of the first column, B plus D is total of the second column, and n is grand total, and factorial A, factorial B, factorial C, factorial D. These factorials are factorials of cell frequencies. Calculate this probability, that is the exact probability of getting this configuration A, B, C, D if A plus B, C plus D, A plus C and B plus D and n are fixed. Check if this adds to 0.05. If it is more than 0.05 or if it is less than 0.05, then two different directions are taken. Yes. you can make a more extreme configuration if possible. A, B, C, D may already be an extreme configuration, but if it is not, then make it more extreme. Your data will speak how to make it more extreme. If A is less, then make it A minus 1, reduce 1 more from this frequency and raise B by 1, raise C by 1 and reduce D by 1. Marginal totals have not changed, because here you are reducing A by 1, here you are raising B by 1, row total has not changed. Similarly, if you are reducing A by 1 and raising C by 1, column total has not changed. So, the row totals and column totals have remained same, and again you can calculate exact probability for this configuration by using the same formula. In place of A, you will now have A minus 1, in place of B you have B minus 1. So, you have new probability, and then add this probability to earlier probability. If that probability is more than 0.05, then you accept the null hypothesis. If the probability is still less than 0.05, then you reject the null hypothesis. Okay. But maybe if it is not the extreme configuration, you may repeat this exercise once more or 2 times more or 3 times more till you get say 0 here. If A was less than B, every time you will reduce 1 from A and add 1 to B, and your configuration will become more extreme. Calculate probability of getting exactly that configuration, add that to previous probability, and if now the probability of getting previous configuration or a more extreme configuration like this has already been more than 0.05, then you accept the null hypothesis. If it is not less, if it is not more than 0.05, it is still less than 0.05, then you go for still more extreme configuration. So, here you get exact probability, here you do not fix critical region, here you arrive at critical, here you arrive at the probability of critical region at some stage or maybe at the end, and the moment or maybe at the end when your exact probability of getting the observed configuration and considering all the possibilities of more extreme configurations is less than 0.05, reject the null hypothesis. And what is the null hypothesis? Null hypothesis is that the 2 attributes according to which total sample has been cross classified are independent. So, rejection of null hypothesis will mean that the 2 are dependent, and acceptance of null hypothesis will mean that A and B 2 attributes are independent. Okay. Chi-square also achieve the same purpose, and chi-square, in chi-square you calculate value of chi-square, look for theoretical value of chi-square and compare the 2. If calculated chi-square is less than tabulated chi-square at 0.05, then you accept the null hypothesis of independence, otherwise you reject it. So, 0.05 is fixed by you, and for that 0.05 value of alpha or p, you find out tabulated value of chi-square and compare calculated value of chi-square with tabulated value of chi-square. Here you are not fixing 0.05, here you are arriving at the probability of rejection of null hypothesis. If the probability of rejection of null hypothesis is more than 0.5, then you accept the null hypothesis. There is a run test. Run test check the number of runs of one. What is run? Run means when you mix up the 2 series, 2 groups or 2 samples, you may find that sometimes values of one sample are followed by values of the other sample, second sample, another sample. So, that or sometimes you will find that several values appear together which belong to one of the two groups. So, when series of one group is followed by series of another group, then you have one run. So, mix up the data and calculate number of runs. Run test check the number of runs of one series followed by another and compare the number of runs with lower and upper critical values. These lower and upper critical values are tabulated for given values of size of first sample, size of second sample. Okay. And again the logic is same. If the calculated value of runs lies between lower and upper critical values, accept the null hypothesis, and if they go beyond lower and upper, they are lower than the lower critical value or more than the upper critical value, then you reject the null hypothesis. Similarly, there is a sign test. Sign test checks whether the positive and negative signs are equally distributed. This is sign test is something like in statistical application, sign test has been used to study fluctuations in a series. Whenever the value of the series declines, you can say negative. Whenever the value of series increases, you can say positive. And if the fluctuations are random, they are not systematic, we expect that proportion of signs will be 0.5. If the fluctuations are systematic, then the signs, number of signs positive or negative will be different from 0.5. Okay. So, by comparing number of signs, number of times signs plus or minus, plus means the value of the series increases, minus means the value of the series decreases. So, it looks at signs, sign test looks at signs, and we expect that plus and minus happens half times, or proportion of any one sign is 0.5. This is the null hypothesis, and if proportion of one sign plus or minus differs from 0.5, for which we can use some tests for the difference between the calculated value of proportion of positive signs or proportion of negative signs and 0.5, then we can use the test for accepting or rejecting the null hypothesis. That okay, suppose your proportion of positive signs is 0.6, you may say that the difference between 0.6 and 0.5 is small and it can be due to sampling fluctuations. So, you accept the null hypothesis that the fluctuations are random, but if it is 0.9, then the logic suggests that fluctuations are systematic. Okay. The last it is Kruskal-Wallis one-way ANOVA, pool the data for all n observations, replace values by ranks in all k groups. So, as in median tests or as in other tests in which we pool the data. Right in the beginning in non-parametric we discussed Mann-Whitney test, and in Mann-Whitney test we pool the data, then in median test we pool the data. Likewise, in this test also we pool the data and then replace values of original variable by ranks in all k groups and obtain mean of ranks for all the groups. Say for jth group, the group number of groups may be 2 or 3 or 4 or 5. R bar j represents mean of ranks of jth group, mean of ranks of j of values in jth group in the pool data. This pool data part is important. Then Kruskal-Wallis test is equal to 12 divided by n. N is the total sample n plus 1, sigma j goes from 1 to k, means for all the groups, n j r j bar square minus 3 times n plus 1. For more than 3 groups and each with more than 5 observations, which will usually be the case. In sociological data, this will always be the case. If you are using Kruskal-Wallis test, it means you are dealing with more than 3 groups, and in each group there are more than 5 observations. So, then Kruskal-Wallis test follows chi square with degrees of freedom k minus 1. So, you can say that kW is actually chi square. In that case, if there are more than 3 groups and in each group there are at least 5 observations. So, and then samples, if there are 3 groups and 5 observations, then sample size is 15. If there are 4 groups, then sample size is minimum of 20. So, if sample size is 20 or more, then this kW can be replaced by chi square, and by fixing 0.05 or 0.01 probability alpha type 1 error, you can find out value of chi square from the table with which this needs to be compared, and the degrees of freedom is k minus 1, number of groups minus 1. So, if you have 4 groups, then degrees of freedom is 3, if you have 5 groups, then degrees of freedom is 4. Thank you. So, what I have tried to say that as a rule this hypothesis testing is about knowing whether the empirical results have arrived due to sampling fluctuations, and they are not indicative of reality in the population. And I must end by saying that all this means that hypothesis testing or all tests of significance apply only to sample data. If you are dealing with census data, then no statistical tests are required. From census data or from study of all the units in the population, just descriptive statistics will do. So, if you take census data and census for India and calculate correlation coefficient between two things, it may be very small, 0.0002, but it is real. Problem arises when the data come from sample studies, and then your correlation coefficient may be 0.2, 0.3, but that may be due to sampling fluctuations and not reflect the true correlation in the population. It is for this purpose that we use statistical tests. Thank you.